So this is just a quick outline. Actually, there's a lot of similarities between Japan and New Zealand. We're both island nations. We have earthquakes and committed to sustainability, and we have quite a few other very similarities between our two countries. Now, before I get into the FAN project, I would like just to briefly explain some of the previous government projects we've had and what led to the FAN project. We had a power quality project, which is looking at power electronics and the impact on power quality in the New Zealand system. And then we had a green grid, which stands for Gathering Renewable Energy into Electrical Networks, which is particularly about PV, photovoltaics. And as a result of these, we went to the government and said, well, we're patching the system up to work, but in a couple of decades, we won't have a very good system. We need to think how we can get a better system rather than patching up for new technology. Now, for us, concept diagrams are actually a key thing for our project. So this is a concept diagram for the power quality. It's got a device stream, it's got a network performance, and we came out with the EEA power quality guidelines, which actually are in effect in New Zealand. And these are some of the supporters, and basically we, after 3 years, released the guidelines. We had 1 year of industry using it and revised on feedback, and then it got set in concrete. And these are some of the outputs from that project, the guidelines and the report, main report. And we had an input into Australia and New Zealand standards. The Green Grid was the next government project, and this incorporated, as you see, generation. And one of the major things we're looking at, of course, is the inverter-based generation in the system. We came up with guidelines for small-scale inverters. We had an input into this ASNZS, particularly the control modes requirements. Now, we know, well aware of these terms, the motivation for, because of climate change, we're trying to decarbonize, we're trying to use renewable energy sources, which at the moment is interfaced by inverter-based systems. So our IEA, they've got their net zero by 2050. New Zealand's come up with the emissions reduction plan, and it's actually a whole set of different industries, as you can see. This is the energy industry, but also transport's affected it because we're looking at going to electrical transportation. So we have an energy strategy in New Zealand, as you see, 2022, and the two parts, phase one, exploring what's possible and charting the path. And that's basically two parts of the FAN project. Local conferences, as you can see, the titles, delivering a net zero carbon energy future, low carbon environment. So let's have a look at the motivation for DC. Well, it comes about because of generation. Wind turbines now, type 4, are basically full power conversion going through a DC stage. We've got photovoltaic. We've got power electronic devices that are developing rapidly, and we've got energy storage. And these all feed into converter and converter systems, needing AC to DC, DC to AC, and DC to DC. So let's have a look. Electric transportation is a big one. Photovoltaic, type 4 wind farms, battery systems, electrolyzers. And when you talk about electrolyzers, most people think of splitting water for hydrogen and oxygen, but there's even a bigger one already operating, and that's in the form of aluminium smelters, which are basically electrolyzers. So here is some of the new technologies that are coming in that are basically DC based. Household appliances are seeing the same LEDs. The fridge freezers shown there are inverter based. They convert to DC and back to AC. And of course, fridges, washing machines and clothes dryers are also DC based. And now you actually can get a heat pump based hot water heaters. So rather than a resistive element, they actually use a heat pump cycle. Industrial loads and large scale generation, again, similar story. A big one in New Zealand is irrigation pumps, but also in factories. So there's a factory there. It's a dairy factory with 1,000 odd variable speed drives, with the biggest one being about 630 kilowatts. Lots of applications using DC. So the question is not whether DC conveyance and DC systems will have a role in the system moving forward, but where it should be used and how it is to be implemented and how far should it be deployed. And these are the questions that the FAN project is addressing. So let's look at the vision for the future. And as I said before, concept diagrams are really important. So this is our concept diagram that we delivered to the government for FAN project. And as you can see, it's a hybrid system. So we have DC in the HV high voltage system, we have some DC in the medium voltage, and we have DC in the low voltage. And that is basically because we see a hybrid system as the way of the future. We're always going to have to change the voltage level because there's an optimum voltage for a given power level over a given distance. And the AC transformer is first of all reliable, it's efficient, and there is a big investment in it. So we are not looking at ditching or getting rid of all the AC transformers. We see their role continuing in the system, but we see the subsystems or DC where it is actually beneficial to make them DC subsystems. So this is really the concept diagram for our project. So just in words, just what I've already said about why we've gone for a hybrid AC-DC. It gets the best of both worlds. And yes, lower losses and less conversion stages mean lower cost and greater reliability. So we're looking at the direct integration of DC-based in it. So our program is a 7-year program. It started at the end of 2020, and probably you'll realize that at that stage, COVID was hitting. So that actually made it very hard to recruit researchers for the project, which has actually slowed in the initial stages. But we've got a lot of development now. We've got a lot of people on board, and we're catching up. So this diagram is basically exploded view of the concept diagram. So we're split into 5 work streams. Work stream 1 is entitled Network Architecture, and the aim is to find out how much of the system should be converted to DC. And in order to do that, we are developing analysis tools for simulating large hybrid AC-DC systems. So basically developing simulation tools and using them to find out what is the optimum amount of DC, where it should go in the system. Workstream 2, we call it, is circuit topology, looking at what type of arrangement should be there for a functional circuit. Where is it earthed? Is it bipole, monopole? How do we protect it? What type of protection? Workstream 3 is converted topology, operation and enabling technology. So it's really a bit of a catch-all because it looks at converter control, converter topology, it looks at control systems, but it also looks at novel things like we're working on low voltage DC breakers using supercapacitors to absorb the energy to allow the contacts to break. Workstream 4 is down the bottom left. I couldn't come up with a nice graphics, but its purpose is to actually look at how do we transition to this new system. The government has given us a target date of 2050 to transform it over decades, and we're looking at evaluating repurposing AC infrastructure for DC, and these are primarily AC cables and AC insulators, using them on DC. There's a workstream 5, which is a local requirement. It's actually benefit the Maoris, to train up the Maoris, but also to be of benefit to Maori communities. So that is a local requirement that we're meeting as well. Now, we actually work on this 2019. Our initial bid went in on December 2019, and then we got invited to put in a full proposal 2020. Now, since we put in and got that, we've actually been monitoring what's happening worldwide in the conferences, papers and that, and I'll just run through them. So there's this interesting paper in May 2020 on DC as the future as an IEEE, proceedings of IEEE. They proposed this system, which as you see in green is actually DC. There was this one in 2021, which is Hitachi ABB Journal, and this is what they say is the traditional. This here is what they actually see for the future, and some of the features are the same as our proposal. Meshed HVDC, MBDC, and different context, and as you see that DC subsystems and actually an AC system. Lots of papers on DC homes. Whenever you look, you'll see lots of them, and even the first sentence there, given changes in how people are using electricity, is AC only electrical system still the right option for residents of the future? And we're saying no, should be DC. and come across this. We've actually got one of our researchers, postdoc, is going to a conference in the USA and will be visiting this house later this year. This is Purdue University. They've come up with a DC house. In fact, we're in the process of converting one of the university houses into a DC house as a test bed showing the technology. So basically there is your low voltage AC traditional system, and if you have a look carefully, you've got a heat pump. The first thing you do is rectify. You have an AC-DC interface here. If you go to DC, you get rid of those stages. You can have something like this. So you just have a DC to DC converters and straight into your electric vehicle. Sigray, as you can see, is starting to produce technical brochures on medium voltage DC distribution systems. And of course, there's plenty of different activity, high voltage DC, and this is just a typical newsletter about all their developments. Even this year, there was a call to highly robust power electronics in the era of DC grids, and also IEEE transaction on power electronics letters. There's also a lot of activity worldwide in terms of groups, and I've got a list. In fact, I've got NEDO here as well. So first of all, there is the Open DC Alliance. There is the FAN project, which is out of Aachen University in Germany. In fact, we've got 5 of their researchers coming to visit us at the end of November, and one of our researchers has been there to visit and have a look at the work, and there is a lot of overlap. In fact, if you look at what they talk about here, this is on their webpage. It's talking about hybrid grids, DC and AC grids, determining and planning principle adapted for DC grids and the repercussions on the system for the overlying and underlying conventional AC grid. And that's exactly what we're doing. Technical University of Dresden is one we've had a long association. They have got an AC to DC project, and it's in phase 2, and we have one of their postdocs coming and spending some time, 3 months, in the first half of next year. Fraunhofer also is doing a lot of work in industrial factories and making them DC. Here's one of your concept diagrams. Now, IEEE Working Group on Direct Current Power Networks. Now, this was an ad hoc committee until the general meeting this year. It actually is now endorsed in a fully fledged working group. Now, I am on it. I would have to say that I disagree with some of the concepts in this one. So in this one here, the concept is end-to-end DC. So I did a presentation on FAN and said we're going for a hybrid AC-DC system, and I was told by the chairman that they don't want any AC in the system. It had to be all DC. So this here is actually some of their concept diagrams from some of their publication. I'm actually on the working group. PhD advertisements. I picked this from last month. You can see how many of the involved AC-DC grids. A lot of positions, and here's another advertisement. And as it says in the briefing, combining Tesla and Edison's will to realize a high, medium and low voltage hybrid AC-DC grids. And that's exactly, as I said, the FAN project. And the idea is to have a reliable power system with high penetration of renewable energy and integration of lots of new technology. So let us move on to the progress to date on the FAN program. Now this is just a diagram of the structure. I've already mentioned the 5 work streams, but this adds some of the key people in it. The ones in boldface are the work stream leaders. So the workstream leader, Ratner, is actually works for Siemens in Erlangen in Germany, Nirmal from Auckland University, University of Technology Auckland, Andrew Lapthorne works at Canterbury, and Tiffany is actually University of Canterbury. And it's got there again just the brief goals of each of the work stream. So work stream 1, we've got a functioning tool, a multi-phase hybrid AC-DC unbalanced power flow simulation tool with all sorts of different types of models for different types of converters and converter configuration. We have a PhD student working on an AC-DC for fault analysis, and we've just started working on a couple of dynamic tools. So one of the things we're working on is trying to get these tools sped up so that they can handle big AC-DC systems. Workstream 2, I've just put a mosaic of some of the publications to give you an idea of some of the things that have been done, like comparison of AC and DC distribution systems for for EV charging. Workstream 3, again, I've taken the approach, just some of the mosaic of some of the papers that are being published on this. If you want a list, there is a list on the FAN website of papers. Now, Workstream 4 is the transition one, so lots of photos of some of the testing, because a lot of the testing is in the high voltage lab or on the actual system. So this is our high voltage lab. It's got a 1.4 million volt impulse generator, 500 kV AC testing transformer, and we've got here a DC test set. Looking at partial discharge and treeing under AC and DC. So here is showing you a tree forming under the microscope, and this here is actually the test setup. This is related to it. This is actually looking at egress of DC into an AC system and the effect of saturation, and this actually has overlaps with the geomagnetically induced currents, which is another thing that's being researched. So we're looking at the effect of different core types. So whether it's a 3-limb, 5-limb, or single phase. This here is again testing basically between under AC and DC. We have done full-scale testing. So what happened in this one here is Transpower disconnected the C electrode of the HVDC link, closed this one here onto the earth grid at the substation Haywards, and operated the bipoles unbalanced, so it injected current here, a DC current. So here's Haywards, here's a map of the South Island, New Zealand, and it's pushing DC currents from here to here with a bit of stray current through the neutrals of some of the transformers. So the transformer at Haywards, we're pushing in DC current in here, a few hundred amps, and this raises the potential here relative to here, and you could get a DC flow. So this is the transformer that we were monitoring and looking at. We not only measured the power quality, but we measured noise and vibration on it. Some of the plots, that's the team. Part of the team actually also, okay, that one there shows the noise measurements. There's another sensor that got put there. We also measured, this is a pickup coil to measure the electric and magnetic fields, mainly magnetic fields under this transmission line going out. These are the AC lines, just seeing if we can detect the transformer saturation. Repurposing AC equipment, this is 33 kV cable testing under DC, and this is testing insulators. A wee bit of finite element modelling has been done to try and verify the test measurements, but not a great deal. This is basically on the Vision Mataranga, which is Workstream 5. Now, one of the parts of this project and one of the KPIs given to us by the government is training the next generation. So upskilling people. We have KPIs regarding having people come here and visit and bring their expertise to the project. We have KPIs relative to sending people overseas to gain experience, and we also have KPIs relative to actually training people in New Zealand. These are summer projects, PhD students and postdocs. So that's a quick summary of some of the masters, postdocs, PhD students and undergraduate student projects. So we've had 62 undergraduate student projects. We also had a boot camp, which basically is when we bring high school students in to actually do some interesting experiments relative to power systems to encourage them into the field of electrical power systems, and particularly the underrepresented groups like Maori and Pacifica students. Now, the government awarded in the end 4 what we call SSIF projects under the Advanced Energy Technology Platform. So that is a category. So there's other projects. One is on heavy transportation, and they're looking at aviation. And the other one is on hydrogen. And why they all interlink is because they all involved electrical power systems. So we meet once a month as leaders of government research programs. We also meet with the government managers every so often. Hydrogen production has a bigger impact on the electrical system. We've got a case study we're working on now at Christchurch Airport. And of course, that hydrogen is basically being looked at for aviation fuel. So the heavy transport one is looking at changing the planes to basically be hydrogen powered through fuel cells and what have you to drive a turboprop. At the moment, they're looking at ATR and doing it, but they're actually looking at the retrofitting and demonstration. So I've got down here, this is the acronyms. SSIF is a Strategic Science Investment Fund, and the AETP is the Advanced Energy Technology Platform. So those basically are the three of the main projects. The fourth one that isn't part of our cluster is working on industrial heat. So in conclusion, we're moving to a DC world. Many advantages and also many challenges to overcome. And of course, DC will have a very important role in the future power system due to the energy transition underway and the technologies available. And we actually, what's been happening internationally, what we've seen in the literature, what we've seen other groups, has actually reinforced our decision, which we actually made in 2019, to go to a hybrid AC-DC system as our proposal for the government. And although initial progress on the program has actually been slow because we having a lot of difficulty recruiting, the COVID restrictions have actually dropped off now, and we're starting to bring in researchers and accelerate the progress on this project. Well, thank you very much.